Today, we're going to continue looking at parameterized curves. In particular, the context that we're going to be doing this in is line integrals. The idea is still the same. It's always the same in integration. We evaluate the expression, in this case, f dot dr, at all the points along in the set described in the integral, in this case, a parameterized curve C, and then we're going to add the results. So the new skill that we need to acquire is how to parameterize a curve. So let's start with some parameterized curves that we're already familiar with. Yesterday, we reminded ourselves of the unit circle. So in addition to defining the two coordinates, cosine t and sine t, we're also saying what values of t we want to plug into our, what values of the parameter are we going to be using. So if the unit circle, cosine t, sine t, for t between 0 and 2 pi will give us once around the circle counterclockwise. So this specifically is going to be once around the circle. Counterclockwise. Starting at 1, 0. So there's a lot of information that's being communicated here. We see what the x and y coordinate, how the x and y coordinates are defined. We see what values of t we're going to be plugging into these functions. And we also find out where the curve starts and ends. So we can see this starting at 1, 0, because if we just plug in the lowest value of t, that's just going to be cosine of 0, sine of 0. Just evaluate the coordinates at the starting value of t. Counterclockwise, because that's the positive direction. That's why you do x is cosine t and y is sine of t. But we got all these points going around the unit circle. So here, the point 1, 0, where we're starting, that's when t is equal to 0. The next point we head to that would be easy to evaluate is at t equals pi over 2. So at the point t equals pi over 2, we're at the point 0, 1. That makes sense. If we do cosine and sine of pi over 2, cosine of pi over 2 is 0, and sine of pi over 2 is 1. So we can see that we're going counterclockwise around the circle, like we normally do. So we can control where the circle is, or what part of the circle we're getting, by changing the values of the parameters that we're plugging in. we can change the portion of the circle by adjusting the parameters. So if, for example, I want to start off at 0, 1 and end at 0, negative 1. If I want this left half, so if I want to start, keep going counterclockwise and end at 0, negative 1. My x and y are still the same, cosine t and sine of t, but I'm plugging in different values of t. In this case, t is going to start at pi over 2 and end at 3 pi over 2. So I'm going to have a cosine of t, sine of t, for t between pi over 2 and 3 pi over 2. That'll get us that left half of the circle. Any questions? The next layer we want to add onto this, since we're doing all this stuff in vectors, rather than just listing our coordinates as a point, what we will do for the parameterization is list it as a vector. I'm just going to keep using this unit circle. So rather than listing as an ordered pair cosine of t, sine t, I'm going to say cosine t is the I and sine t is the j. And then I can give the vector name to our curve. So I can list the parameterized curve as a vector. Questions? How's everybody okay? Everybody looks stunned because it's vector calculus. Thinking, shouldn't we have a midterm at this point? It's the middle of the term. I don't think we're going to do that in class. We're going to do that on campus. And it won't be called midterm. It will just be a bunch of quizzes. The sum total will be a midterm, but I'm never going to tell you that. It's just going to say quiz. That way you won't be too worried about it. If I write exam at the top of a quiz, then everyone's like, oh no, it's an exam. But if I write quiz, that's less threatening. So what we want to do is use this vector parameterization of a curve and see how that's going to show up in a line integral. Notice that one of the parts of the line integral, we have the integral over C, the curve C. So that's where we're going to list all these points somehow. Then we have the vector field F dot dr. So it's not a coincidence that I listed the line integral with dot dr and started calling my parameterized curve R. So once we've parameterized our curve, the dot dr part, if you recall, would be the direction that the curve is going. We need to make a dot product with whatever vector is happening from the vector field and a dot product with the direction that the curve is headed. So I need to take this R of t vector and describe where it's headed. It's called dr, and this is r. So if you were guessing that we're going to take the derivative of this vector, you were correct. And specifically, we're going to find the derivative of r with respect to t. So the derivative of cosine is negative sine, and the derivative of sine is cosine. And then we're going to make a move similar to what we did when we were doing substitution, the substitution method back when we were integrating. I'm going to solve this expression for dr, and that's what's going to show up in my line integral. Once I write the expression for dr, we can see that our line integral is going to become an integral of a function of t dt. So we're going to be integrating over a bunch of t values. We're going to integrate over a bunch of t values. So now the line integral is going to become an integral dt. It's going to be a simple integral, so we just have to integrate from the starting value of t to the ending value of t. Questions? So let's use this curve and set up a line integral. All right. So let's come up with an example. What we need for an example is a vector field over which we're going to integrate. I realize that we don't have a lot of context for what's going on. We're just working on our calculations. We did this a lot in Calc 2. We're like all area under a curve, then spent a whole chapter learning about techniques of integration just to see how we push the symbols around the page. Same thing here. We're learning how to push some symbols around a page, keeping in mind that we're calculating a dot product. So if we want applications of this line integral business, we just have to think about integrations of applications of the dot product. So let's make a vector field. my vector field is going to be 2xy I plus y squared j. And C is going to be the unit circle once around, counterclockwise, starting at 1, 0. We know that this is just going to lead to an integral dt. So let's see how that happens. We have our vector field. That's easy. We need to get a dr, and we need to describe this set of points in a way that the integral will understand. So we need to parameterize the curve. So C, we can parameterize C with R of t is cosine ti plus sine tj for t between 0 and 2 pi to go all the way once around, starting at 1, 0. Here's what we get when we get the parameterization. When we say that R of t is cosine ti plus sine t times j, I've defined what x is equal to and what y is equal to. So here we're saying that x is cosine of t and y is sine of t. So there's x equals cosine t, y is equal to sine of t. We're going to need these because one of the things that we need to do is evaluate the vector field at all the points on this curve. So I've got to be able to describe all these points on this curve to the vector field so the vector field will know what values it's supposed to have. So we're going to need this to plug into the vector field. The other thing that we're going to need is the .dr part. And so that's just going to be dr is going to be the derivative of r with respect to t. The derivative of cosine is negative sine. The derivative of sine is cosine. And this will all be multiplied by dt. Now we're ready to set up our line integral. We've got all the pieces. The vector field 2xyi plus y squared j. We evaluate that at all the points on the curve itself. So x is cosine, y is sine. So my integral over c of f dot dr. So I'm going to take f and evaluate it at r. So f is 2 times cosine of t sine t times I plus sine squared times j. This first piece is evaluating the function, the vector field at the points on the curve. We make a dot product of this with dr. dr is minus sine of ti plus cosine of t j dt. Now that our integral is just a dt integral, it says what values of t are we going to be using in this calculation? T starts at 0 and ends at 2 pi. And we see the same instructions that we always have for integration. Evaluate the expression at all the points in the set, then add up the results. It only sounds weird to say because we're doing a continuous sum. Notice that we've got two vectors, but the vectors are in a dot product. So when I find the dot product, I'm going to end up with a scalar function. Dot product is a scalar product. So what we get is the integral from 0 to 2 pi. And then we just write the dot product. 2 cosine t sine t times minus sine t. So minus 2 cosine t sine squared t plus sine squared times cosine squared right. We're just finding the dot product, evaluating the expression at all the points on the curve. In this case, the terms happen to work out to be like terms. So we've got the integral minus 1 cosine t sine squared t dt. The line integral is going to be a sum of dot products. That means our line integral should produce a scalar, and now we have a way to get at that scalar. Questions? How's everybody okay? It's just mechanical. We're not worried about what this number represents. We don't have a context for why we would evaluate this dot product. We don't know what the vector field represents or why we're evaluating it over the circle, except for the fact that that's the one that we know right now. But now we can integrate. And this one happened to work out to a nice integral that we can integrate. So we'll get minus 1/3 sine cubed evaluated from 0 to 2 pi. So we get 0. So from a certain point of view, we did all that work for nothing. But that doesn't mean that we got nothing. We learned that this quantity is equal to 0. It's like when you're playing Wordle and nothing comes up. They all come up gray on your first guess. It's not that you didn't learn anything. You learned 5 letters that weren't in that word. You always get something. Questions? At this point, you might be suspicious. You might be thinking, Leach, did you make this easy on yourself? And Michael, absolutely. What do I want to do up here? Difficult integrals? Make this work out to like cosine squared? So we can't do a substitution? Nah. Let's just make it work out to a substitution. Any questions? Also, this saves me from having to pull out the calculator because this is just a simple integral. It's just an integral dt. It's a definite integral. It's got a starting and an ending point. So we could have just put this into a machine if we wanted to, or if we had to. Is everybody okay? Everybody looks stunned because this is so simple. Like, oh, dude, there are whole books on vector calculus. And it seems so simple. Once we have the concept, once we have the concept, we understand what integration is supposed to represent. Integral, evaluate the expression at all points on the set, then add the results. We just have to go looking for more curves to parameterize. We just have to practice the skill, parameterize curve. We just have to practice the skill, what's this vector field look like? And then we just have to go looking for applications of the dot product that could show up in a line integral. Recognize that line integrals are constructed on dot products. It's a dot product that's sitting in the expression. So applications of the dot product are going to be our applications of line integrals. This was a lot of stuff at once. So as far as storytelling goes, this is the kind of story where you see what happened at the end, and then it flashes back to the beginning, and you catch up to that point. So it says, here's something that's gonna happen an hour into the movie. And the audience is like, oh, gosh, I wonder how we got there. And so that's kind of what we did. We started off with line integrals, which is a couple chapters in. We've got to talk about vector fields and parameterizing curves. But we want some context of where things are headed. Otherwise, it's just a random sequence of events. Sometimes it's difficult to linearize a story. Just have a beginning and an end. And as the more mixed up the topics are, or a story, like a class, when we tell the story of math classes, it's sometimes difficult to put those into a sequence. So for those of you who've been through linear algebra, you went through linear algebra in a particular order. But that class could start anywhere. You could start with linear systems. You could start with vector spaces. You could start with matrices. It's all connected and it all happens all at once. So with linear algebra, depending on how modular the book is written, you can start at any chapter and work your way out. A very similar thing happens in trigonometry. So you can start your trigonometry class with right triangle trigonometry. Sine is opposite over hypotenuse, cosine is adjacent over hypotenuse, tangent is opposite over adjacent. And then use that, and then move that into the unit circle. Or you could just start off with the unit circle approach and go back to right triangle trigonometry. It's however you want to frame the class. How do you want to tell the story of trig? Because all the events are happening at once. And on one hand, that's what makes it difficult. On the other hand, that's what makes it easy. Because everything is connected. Let's do an example where we parameterize a function. I'm selling these parameterized curves as another way to describe curves in R2 or R3. One of the things that's going to be required then is that it needs to be backwards compatible. I need to be able to take a curve that we described with a function and now describe it with parameterizing. So, for example, what if y is a function of x? Y is equal to x squared. If we want to parameterize a function where there's already a relationship between the variables, that's even easier. We're going to make functions of x and functions of y, or we're going to make x and y functions of t. And the easiest thing to do, just make x equal to t. Since y is a function of x, just say x of t is just t. Y of t is then t squared. And if I want to get this whole parabola, if I want the whole parabola, just do this for all t. One thing to note, when we parameterize a curve, we assign an orientation to the curve. We assign a direction to the curve. If I parameterize the curve y equals x squared, with x of t equals t and y of t equals t squared for t going from negative infinity to positive infinity, then I'm giving it a left to right orientation. So this parabola has the shape of a parabola. When t is negative infinity, will be on this side. And when t is positive infinity, will be on this side. So this is the orientation of that curve. It's just following along the standard x goes from left to right. So if we want to adjust things, if we say, hang on, I don't want x to go from left to right. I need to go from right to left. If I want to switch the orientation, I'll just reverse the direction. I'll just reverse the direction of the x-axis. Now we're going to get the same parabola, but negative infinity will say positive infinity. Positive infinity will say negative infinity. And we have just changed the direction of our parabola. We changed the direction of the x-axis. questions? So there's a lot to think about when we're parameterizing a curve. First, we got to make sure that we get the shape correct. Then we got to make sure that we get the orientation correct, get the direction correct. And then we have to make sure that we start and stop in the place that we want to start and stop. That's everybody okay? Right. Right now, it looks strange because we're still parameterizing curves in R2. And we have lots of tools for describing curves in R2. I just did a parabola and a circle. Y equals x squared. One of them is a function. The other one was an equation, x squared plus y squared equals 1. Where this is headed next is that we're going to have to parameterize curves in R3. So rather than a curve just being traced out on a flat piece of paper, we could have a curve running through R3. So imagine a fly flying through the room. The path of the fly is an oriented curve in R3. It's just a one-dimensional thing. The fly is just going to go forwards and backwards. Now the fly is just going to go forwards, but we can trace back along its path. We need some way to describe a one-dimensional set in R3. And we're going to do that with a parameterized curve. If I try to make z a function of x and y, that's going to give us a whole surface. That's not what we're looking for. That's a two-dimensional set in R3, and I want a one-dimensional set in R3. So we're going to have to get used to parameterizing functions in R3. How's everybody okay? Too simple? Once we factor out the big idea of integration, we just want to start looking for that big idea in other places. One of the difficult things to see here, changing the direction of the x-axis. So it makes sense that we can just multiply by -1. Multiplying by -1 makes opposites. So it's going to change the direction of the x-axis. A lot of times when we first start studying functions, we don't think about the relationship between, say, f of x and f of -x, or f of x and f of 2x. What is that? What does that do? We get a little bit of that in trigonometry, where we see the sine of x has a period of 2 pi, sine of 2x has a period of just pi, because the x's are going twice as fast. So putting a negative just makes the x's go in the opposite direction. All right. That's going to do it for today. That's parameterizing curves in the context of line integrals. We're just going to parameterize some more curves, but not until Monday. There's not going to be a meeting tomorrow. So I know everybody will be super disappointed that there's no Calc 3 meeting on Friday, but I'm not able to hold a meeting tomorrow. So everybody, that'll do it for this week. I'll see y'all on Monday. Everybody have a good weekend, and thanks for playing.